Now we look at some strain and stress results. I switch the part type to apply. We look at the results for all element types. Result contour is strain. In the laminate coordinate system, at the inner surface of the element and in the hoop direction. When using the graphical results, strains in the hoop direction are not clearly seen as we have a free edge effect here. So we better use line chart. Line chart shows that the strains at the cylindrical shell section are in the range of 0.6 to 0.7%. And when we move towards the pole of the dome, strains are in the range of 1%. Next we look at the strains in the axial direction, again using line charts. Now we focus on the transition region. One can see that the strain oscillates between minus 0.4 and 1% in a very short distance. The behavior is better depicted using graphical results. We zoom into the location and use a scaling factor of 10, for example. Clearly, the design needs to be modified due to this local bending effect, where the strains are +1 at this region and minus 0.4 at this region. Next, we look at the stresses in the out-of-plane normal direction. Part type is ply. Result contour is now stress in the laminate coordinate system, and the stress component is Z. Line chart shows that there's a local peak in the dome region, the value being 125. If I switch the reference plane to the outer surface of the element and repeat the line chart, now the stress peak has leveled to the 75 MPa, and this is quite interesting. I change the part type to laminate, result contour to stress and sigma Z, so I'm visualizing the same result as previously. Inner surface is now the reference plane. If I zoom in here, this is the interesting location here, one hotspot element. Now that the part type is laminate, I can make a post-processing in cross-section wise. And if I pick the laminate cross-section 55, I'm in this critical location. So when the inner surface of the element is the reference plane, it's 127 MPa, the stress. And when the outer surface is the reference plane, 76.3 is the stress level. So really high gradient over this element. If I switch the contour to material, one can see that there is there are two resin filler elements in this region, and this is partly the reason for the high stresses in the neighbor lamina. I have prepared another study and to study this stress concentration issue more, and in that second study I have increased the number of elements by defining that the element length is 1/4 of the one I used in this model. Also, this material 4, light green material here, I have modified so that I have divided the thickness of the material by 2, and simultaneously I have duplicated the amount of material in this region. So with these modifications I have more dense mesh in this region. So 55 was the laminate cross-section of our interest, and the thickness in this region is 7.2 millimeters. In this updated model on the left-hand side, the model at this location has the same thickness. Now I look at the stress results in the laminate coordinate system inner surface in Z direction, and 98 MPa is the stress level. Inner surface, outer surface 89 MPa. So the stress gradient over the bottom and top surfaces of the element is now much lower, and these results here can be considered more reliable.